So last time we talked about ion implantation and the dopant profile. The dopant profile for the ion implantation given by this Gaussian distribution. So it's given by this formula. And we have went through those slides. And now we'll continue with the junction depth in the silicon. So here we have this Gaussian distribution. This Gaussian distribution dopant profile is given by this formula. If we set this formula equal to MB, so MB is the background doping, then we do the derivation. So finally, we can find out the junction depths. There are two junction depths. You can see plus, minus. So we have this one, junction 1 and junction 2. So sometimes, if x J1 larger than 0, then this one will not be a valid number because in this case, the actually 1 will be here. This is not a 0 junction. And now let's look at another example. So we have 200 kilo electron volt phosphorus implanted into a p-type silicon with this background doping. A dose is 10 to the power 13 per square centimeter. So from the graph here, so 200 electron volt phosphorus, so we can find out the depths and the standard deviation. So we find out the RP, the production depth, and the standard deviation given by those numbers. So first, find out peak concentration. So peak concentration is given here. So MP is given by this formula here. So this comes from this formula. So we know the peak concentration is given by this number. The junction depth. So if we know the RP and delta RP, then we know the expression of this dopant profile. So we just set this expression of the dopant profile to be equal to CB, to be equal to the background doping CB value here. Then we find out a junction depth. So we have two numbers, one near the surface, one well below the surface. Find the sheet resistance. So we have talked about the sheet resistance from chapter 7. For the sheet resistance given back here. This formula here. So RS equal to 1 over Q mu Q. So Q is the dose. The Q is the total carrier per unit area is the dose. Mu is mobility. Q is the charge. So we have here. So we have the Q. So we have the Q equal to this number here. Mobility. The dose is given by 10 to the power 13 is given by this number. So normally we know that for the electron, the mobility is about 1,500. But in this case, so we have this is the highway doping. So when we have the highway doping, the mobility is much lower than this value here because of the scattering of the electrons by the dopant items. So it's only 350 here. Then we get this sheet resistance. So in reality, this is not a very useful concept because if you measure it, for example, you measure you apply voltage here, and you have the current flow in and current flow out. So the current will flow like this. So what you measure is the top layer, because the current, you may think current may flow like this, but this will not happen. Because so either this p junction or this p junction. So one of the two p junctions will be reverse baggage. We know that when we have reverse baggage, the p junction is not conducting. So it is possible to have the accommodate doping profile using ion implantation. In this case, we use multiple implants. So we have 24 keV. So we have different energy and also different doses. So in the end, we can get this kind of doping profile. And that's why this is much more powerful than the diffusion doping, as we learned from the chapter 7. For the diffusion doping, the only dopant profile we can get is this one, ERFC, error function, complementary error function. But for the ion implantation, we can have complicated doping profiles. So we know that after implant, we always need a high temperature annealing process. So during this high temperature annealing process, the dopant, the implanted impurity will begin to diffuse. For example, when this is implanted, so after further diffusion, it becomes this blue curve. So we start with the red curve by implantation. After diffusion, we form this blue curve. So we know that this red curve, this one is Gaussian. This is Gaussian. And also we have shown that the Gaussian after diffusion, so this one will also be Gaussian. For the Gaussian, what we need to know is the dt value. And we know that dt is d1 t1 plus d2 t2, as we learned from the chapter 7. So we have this one. So the total dt value is the sum of d1 t1 d1 t1 d2 t2. So now what do we need to know? We need to convert. So we have this profile. So we have this profile after implantation. So this one corresponds to this red color curve. So we compare this profile with this Gaussian distribution with the dt value here. So we compare those two. So you can see that so the 4 dt, we say d0. So 4 dt here is the same thing as this part here, equal to 2 delta rp squared. So they have the same value, they have the same meaning. Then we have this one. So d0 t0 is given by this number here. So then we know that dt will be d0 t0 plus dt. So then in the end, so we have this formula here. So basically, so we have this one equal to 2 square root delta rp squared plus dt. Then we have this one, then we times 4 in the front. So then we times 4 in the front. So in the end, this one should be so d0 to t0 equal to 1 over 2 delta rp squared. So d0 to equal to 1 over 2. So this one will be 1 over 2. So in the end, so we have this formula here. This is the total dt value here, and we have similar dt value here. This way, we can find out the dopant concentration after a further diffusion. So now we look at the mask thickness and the lateral. We look at the mask thickness. So here we have the mask. So we assume that inside the mask, we also have this Gaussian distribution. So we have this Gaussian distribution inside the mask. So here we use the star. The star means for the value in the mask layer. So we have delta rp star, rp star. So we have this one. So the one requirement is that the dopant concentration here, this C star M here, should be smaller than the background doping. In order not to significantly alter the doping concentration. So we want this number here, to be smaller than CB. Then we do some calculation. So we have this value here. So this M equals to this part. So this is the first requirement. For the second requirement is the dose penetrated into the mask. So the dose penetrated into the mask. So this one is given by this formula here. This one we do the integration from xm into infinity. So then we have this part inside here. We do the integration here. In the end, this is the complementary error function. It's given by this value here. For the rule of thumb, the good masking thickness is given by the mask thickness should be rp plus 4.3 delta rp. So in this case, so qp will be given by q over 2. So inside it is given by 4.3 square root 2 equal this one. So this is equal 10 to minus 5. 10 to minus 5 cube. So that means the dose get into the substrate is 10 to minus 5 of the total dose. The concentration at this point, relative to the concentration at the peak. So the ratio between the concentration here and the concentration here is given by E minus 4.3. So when we have xm equal this number here, we put into here, is given by 4.3 divided by 2. So we have 4.3 squared. This is given by 10 to minus 4. So the dopant concentration into the mask is 1 over 10 to the power 4. of the dopant over the peak of dopant concentration. Now here's the example for the mask material thickness, but in this case, the dopant, this number here, is given by this one. So this is 10 to the minus 6, 10 to the minus 6. So what do we see here? What do we see here is 10 to the minus 5, 10 to the minus 5. So here, the value here corresponds to 10 to the minus 6, the dopant that penetrates, transmitted into the substrate. So as you can see, the higher the energy, the thicker mask we need. The boron is light. So we have the boron, we have lighter ions, and it can go to a deeper. So we need a thicker mask material than phosphorus and also more than arsenic and antimony. But those numbers here, but they are different. But if you look at the number here, you can see antimony and arsenic are pretty much the same. So they have pretty much the same dp depth, pretty much the same depth. At 100 keV, antimony is higher than arsenic. At 200 keV, arsenic is higher than antimony. But this is for the case of the silicon. It's for the case of silicon. So what do you see the value here? We have all the star here. So this is the star. So what do you see the value here? And this is also RP star. So these are for the mask. So the value here is for the mask material, not for the silicon. That's why you can see it's different from the silicon. They are different. So this is the polysilicon, silicon oxide, silicon nitride. So aluminum resist can also be used as the mask because this is ion implantation is done at the room temperature, so the resist is good. So now we look at channeling effect. So this is, if we look at silicon lattice at different orientations, this is along the 110 direction, 111, 100. You can imagine if the ions is penetrated, it gets along the channel, there may be some effect. But for this one, random tilt and rotation, so there will be no channeling effect. So here, the channeling effect occurs when ion velocity is parallel to a major crystal orientation. It's parallel, or maybe we should say nearly parallel. In this case, then some ions may travel considerable distance with little energy loss. So once in the channel, ion will continue in that direction, making many glancing collisions. That means glancing means that the angle here, theta is very small. So theta maybe is very much smaller than say 10 degrees, for instance. Very small. So the angle is very small. This is glancing angle collisions. So you can see here how many you can see here. This is the phosphorus impurity profiles for 40 keV ion implantations. So silicon at various angles from 110 axis. At 0 degree, it goes to this long. This is like 800 nanometer. At 8 degree here, it comes to about here. This is about 0.2. You can see this is 200 nanometer. You can see because of the channeling effect, it goes extra about 600 nanometer. So because of the channeling effect, we go extra 600 nanometer deep. We know that the lattice here from here to here is about 1 angstrom. The lattice is the order of 1 angstrom. So you can see, so we have how many glancing angle collisions. So we say this is 600 nanometer equals 6,000 angstrom. Is only 1 angstrom. That means so we have 6,000 order of 6,000 glancing collisions before it comes to a stop. So how to get rid of the channeling effect? The first one we call the oxide layer. So this is amorphous. So when we have amorphous materials, so the ions will be randomized. So the ion come here, they become randomized. Another way we do the 7 degree tilt. When we do the 7 degree tilt, there will be no channeling effect. Here you see, here we have 8 degree, but here we have 7 degree. The third way, we damage the top silicon, so we can destroy the lattice before the implantation. So we do a high dose silicon implantation to convert the surface layer into amorphous silicon. So we convert into amorphous silicon, then we do the implantation. So the idea is similar to here. This one is also amorphous. This oxide is also amorphous. And now we look at some modeling. So when we have the ion implanted into the silicon, so the ions are stopped at the random positions. So mostly not in the crystalline set, so that they are not active as dopant. They will not contribute to electron or holes because they are not active. So now let's look at how the ions get stopped. How the ion gets stopped. That means how the ion will lose energy, will energy loss of the ions. So in 1963, those three people here, LSS theory, those three people here, they proposed that the energy loss of each ion can be divided into two independent processes, namely nuclear stopping and electronic stopping. This is the nuclear stopping. That means the ions, for example, the boron ion, collide with the silicon atom, then it will be stopped. This is like a two-particle collision. A two-particle collision, so energy loss is given by this formula here. M1, M2 is the mass of the ion and the silicon. This is the atomic number. Atomic number is related to the M. It's related to the mass of the atoms given by this one. So for the ions, for the silicon atom, it can follow speed up to the sound speed. So the silicon atom can follow the ion speed up to the speed of the sound. So this is the sound speed is the characteristic speed of the lattice atom that can follow. For the solid is about 1,000 meters per second. So when the ion is below 1,000, below a few thousand meters per second, so the silicon can follow. Otherwise, if the ion moves so fast, so silicon cannot follow, the energy loss will not be important. So the second one is electronic stopping. In this case, because electrons can follow the ion, the field by the ion, up to optical frequencies. So with velocity 10 to the power 5 meters per second. So this 10 to the power 3, this 10 to the power 5 meters per second. That means electronic loss dominates at higher energy velocities. When the ion has high velocity, nuclear cannot follow, but electrons can follow. So the energy loss is caused by the drag. So when you have this ion collide with electrons, the ion will move forward. There will be a lot of electron cloud following the fast moving ion. So the electrons will drag the ions back. This is how the energy lost by the electrons. But because the ion mass is 10 to the power 5 electron mass, right? The mass of ion is 10 to the power 5 of electron mass, so that this energy loss is not so significant. It will take many drags, then before it gets to rest. So this energy loss is proportional to speed of ion. So speed is proportional to the energy square root of E. And now let's look at the formula by this RSS theory. So the energy loss is proportional to N. N is the target atom density here. So then we have this nuclear stopping power and electronic stopping power. So the nuclear Hn is defined by the stopping by the nuclear, He stopping by the electron. So the ion range, how far it will travel, is given by dx 0 to r. So we have dx here. So you put the dx to the right side, and you put those things to the left side. So you have this one, 1 over n. You have dE over SNE, nuclear loss and electron loss. So the conclusion is that for the lighter ions at high energy, so this has high velocity. So when we have high velocity, more electronic stopping. For the heavier ions at the low energy, that means heavier ions at the lower energy, this is the low velocity of the nuclear low velocity of the ions. We have more nuclear stopping. So this is because, as we said before, so the nuclear cannot respond to ions when it is very fast, moving. And also, only nuclear sloping cause damages such as displacement of the target atoms. So electronic sloping, electron follow the ions, does not cause any damage. So here, for example, when we have this hydrogen ion, this is very light, electronic sloping dominate, there will be damage only near the end of the ion range. So when it become slow, we have lower energy. The same for the boron. Boron is also electronic sloping dominant. There will be damage only near the end of the ion range. But for the arsenide is heavy ion, so low speed, but the nuclear sloping dominant. There will be damage throughout the ion range. So here is the electronic and nuclear sloping power. We know that for the electronic sloping, it's proportional to the square root of E. So here we have energy, square root of energy. So you can see this is the linear. For the electronic, so we have this linear to the square root of energy. For the nuclear, the higher the speed, the lower the sloping, so it goes down. But when the power is too low, the energy loss will also be not bad. So we have this peak here. Then we get this one. We get this the lower down, slow down. So here is the nuclear and electronic component for the in silicon dopant. So we have the arsenide. For example, for the boron, so boron is light, electronic sloping dominant. For the boron, electronic sloping is here. This one. The nuclear sloping is here. You can see the electronic sloping is always higher than nuclear sloping. So the crossover happened at 17 electron volts, but actually 17 electron volts. But actually you can see this drawing here, those two, they will cross here, maybe 7 electron volts. So the number here, the numbers here is a little bit different from the number here. For the case of arsenide, so here we have this nuclear sloping. Number is bigger than this arsenide, this curve here, and this electronic sloping. The crossover happened here. This one is given by here is 700 electron volts. That will be so the energy here, the E2, when they are the same, happen at 700 electron volts. But here, the E2 is given by 800 electron volts. A little bit different from different sources. And now we look at damage caused by the ion implantation and its repair. So we have, and we see that there will be damage near end of the ion range. So near the end of the ion range. For the light ion, there will be damage near the end of the ion range. So this is what you see here is end of range damage. So we see the damage along here. This is near the end. So they go through here near the end. So we have the damage. So the threshold of energy for displacement energy is ED. For the silicon, this is 15 electron volts. So for silicon, we have 4 bonds. So we need to break the 4 bonds in order for this one to become like an interstitial. So we need to break the 4 chemical bonds. So break the 4 chemical bonds, energy is about 15 electron volts. So the number of displaced atoms created by the energetic particle is on the order of N equals En over Ed. So Ed is the energy needed to create one defect. So En is the energy lost in a nuclear collision. For example, when we have 30 keV arsenide ion, 30 keV divided by 15 electron volts, we get about 1,000 displaced atoms. The number will be less for 30 keV light ions because in this case, the energy will be mainly lost by the electronic sloping, not by the nuclear sloping. So as we see before, the main disadvantage of ion implantation compared to the diffuser doping is the production of the lattice damage. So there can be a vacancy interstitial, which may evolve from simple point defects into the complex dislocation and voids. So eventually, implantation will lead to the amorphous silicon structure to make the silicon amorphous. So most damage can be repaired by the high temperature annealing process. But this annealing cycle for 30 minutes at a high temperature, this can cause considerable spreading over the implant by the diffusion. So now we look at amorphous. What annealing needed to make the silicon amorphous silicon? So if the dose is high enough, the implanted layer will become amorphous. The dose required to produce an amorphous silicon layer is called a critical important dose. You can see the higher the impurity, the lower dose that is required to create amorphous layer. So from this graph, if we talk about the room temperature, we have this value equals about 3, so we have here. Then we have this value here, something like this. So for the antimony, so we have this dose to make it amorphous. For the phosphorus, we have this dose to make it amorphous. But for the boron, you can see it never comes to amorphous, unless if we have the lower. So we have the lower temperature. For example, if you look at here, then the boron can also make amorphous. So effectively, we have a lower temperature. It's more difficult for the lattice to get to self repair. But when we have lower temperature, it's more difficult to self repair the lattice defect. That's why we need a lower dose to make it amorphous. So normally we do the annealing step using under argon or nitrogen or vacuum environment. A typical 900-degree 30 minutes will do 3 things. First, restore silicon lattice to its perfect crystalline state. Secondly, put the dopant into silicon substitution set for the electrical activation. Third, it will restore the electron hole mobility. Know that the lattice become perfect again, so the electron hole mobility will be restored. So there are three advantages. First, repair the lattice. Second, activate the dopant. Third, to improve the mobility, restore the mobility. So for the mechanism of this lattice repair, when the surface become amorphous, so when the substrate has been made amorphous, we can use solid phase epitaxy to repair the damage. So in this case, the crystallinity is repaired by the solid phase epitaxy, so where the crystal reforms using the underlying undamaged substrate as a template. That's why it is called epitaxy. So here we have the amorphous silicon, and here we have the crystalline silicon. So this crystalline silicon will guide the growth of the single crystal silicon along the interface. This is the epitaxial process. So the silicon grows on the crystalline silicon substrate. So because of the high activation energy required to annihilate a defect, we need 5 electron volts to kill the defect. It's often easier to regrow the crystal from amorphous layer via this SPE process, because the activation energy is only 2.3 electron volts. To recrystallize the amorphous silicon from single crystal silicon, we need only 2.3 electron volts. But to kill the defect, we need 5 electron volts. So this is like you build a house. You have the house. If the house is damaged, sometimes if the damage is too severe, it's easier to turn down the house. Then you rebuild the house, then to fix it, something like this. So as you can see here, so when we have this dose here, this lattice doping is we have this lattice doping. It is still crystalline, so we need say 550 degree to get 80% repair. So when we have higher doping, we need higher temperature to have 80% active, to have 80% dopant active. But when we have even higher, this is 10 to the power 15, this 10 to the power 14. So when we have even higher dose, it becomes amorphous. In this case, we only need a little bit more than maybe 520 degrees to repair the lattice. We can see it's easier. So here is the same thing. So this is for the phosphorus. So when the So when the dose is very high, it emits to amorphous, then we need lower temperature for the repair. For the boron, when we have higher dose, we need a higher and higher temperature, because you can see here, for the critical boron, it never becomes amorphous. We have room temperature, you go up. You can see the boron will not make silicon amorphous even for very, very high dose. Then to fix the defect, we need a higher and higher temperature. And lastly, we talk about a rapid thermal processing or annealing. So we know that when we have this a high temperature process, the dopant will diffuse. So to minimize this unwanted diffusion, we can use rapid thermal processing. It's also called rapid thermal annealing. We know that the spread out is given by dT value here. So D depends on temperature. So we need a high temperature annealing to fix the defect and activate the dopant. Then what we can do, we reduce the time. We can reduce the time to have smaller dT value. This is the idea of the rapid thermal processing. So here we use like a 30 minutes. But when we do the rapid thermal processing, this will take under 5 minutes, much shorter time. Maybe even under 2 minutes. Very fast. So then the heating is done by the light. We can use the high power laser for the rapid heating source, high power laser or electron beam or high intensity halogen lamp. Here we have the high intensity lamps for the when we have the lamp, the heating will be very fast. But then here we have the fiber optic temperature Celsius. We use the light, we use the spectrum to measure the temperature. This is the photo of this rapid thermal annealing process. So this machine is pretty popular here, at the University of Waterloo. We also have this machine. Thanks.